Before we go through the operation of the circuits, let's take a look at the components. The bucket spool and detent assembly have been removed, as well as the circuit relief valves. A load check valve is located under the plugs at the center of the valve. This illustration shows the basic loader valve components and oil flow with the bucket and boom spools in the hold position. Incoming oil flows past the system relief valve, through the open center passages of the bucket spool and the boom spool. The bucket spool has priority over the boom spool in this style valve. When the bucket spool is actuated, it blocks the flow of pump oil through the open center passage and directs it to the bucket cylinder. When the bucket spool is feathered or is placed in hold, pump oil will flow through the open center passage around the bucket spool to the boom spool. If both the bucket and boom spools are placed in hold, as shown in the illustration, pump oil flows around both spools and empties into the return oil passage and flows back to the reservoir. The bucket circuit has two combination circuit relief and anti-cavitation valves, one for each end of the bucket cylinder. The boom circuit has only an anti-cavitation valve in the passage supplying the lower rod end of the boom cylinders. When the bucket spool is moved out to the dump position, the flow of oil through the open center passage is stopped. Oil flows around the spool and immediately builds pressure sufficient to overcome static line pressure. It opens the load check poppet and flows out the port to the rod end of the cylinder. This forces the cylinder to retract, causing the bucket to dump. Oil from the head end of the cylinder flows back through the bucket spool head end port. From here, it's directed by the spool to the return passage where it flows back to the reservoir. If the load tries to dump the bucket faster than the pump can supply oil to the cylinder, cavitation will occur in the rod end. Under these conditions, the anti-cavitation valve on the rod end of the bucket spool will open and allow pump oil to be supplemented by return oil. When the bucket spool is shifted into the roll-back position, the oil flow to the cylinder would be opposite of what is shown here. The pump oil would be directed to the head side, and return oil would come from the rod side. The valve components which control oil flow in the boom circuit include the spool and detent assembly, which are located at the upper end of the valve housing in the photo. A plate, wiper, and seal are located at each end of the spool. Located on the left side of the valve housing is the anti-cavitation valve assembly, which protects the lower rod side of the boom cylinders. The load check poppet for the boom circuit is located under the plug over the boom spool bore. The plug opens to the center of the wishbone passage. With the boom spool in the lower or power down position, oil passes around the boom spool, opens the load check poppet, flows through the wishbone passage, then out the port to the rod end of the two boom cylinders. This forces the cylinders to retract, causing the boom to lower. Oil returning from the head end of the cylinders is forced to flow through the throttling grooves in the boom spool before it reaches the return passage. This restriction to flow controls the speed of drop and reduces the possibility of cavitation at the rod end of the boom cylinders. The rod end of the boom cylinders is protected by an anti-cavitation valve. It operates when the boom spool is in the lower position and the load causes the boom to drop faster than the pump can supply oil to the cylinders. This happens especially when the engine and pumps are running at a low RPM. Ordinarily, return oil flows around an annular groove at the front of the anti-cavitation valve on its way to the reservoir. But when line pressure drops, return oil pressure operating on the small working area at the front of the poppet causes the poppet to open as shown in the illustration. This allows return oil to supplement the low-pressure pump oil flow to the rod end of the boom cylinders. When the boom spool is shifted to the raise position, the flow of oil to the cylinders would be reversed. The pump flow will go to the head side of the cylinders, and return oil will come from the rod side. When the control lever is moved to the float position, The spool is positioned so that incoming pump oil can open the load check poppet and flow simultaneously to the rod or to the head end of the boom cylinders. Oil not needed for the boom circuit flows around the spool to the return passage. In float, the flow to the return passages at the ends of the spool is blocked. Instead, oil is allowed to flow from one end of the boom cylinders to the other through the wishbone passage. The float position is desirable for cleanup work. In float, the bucket will follow the contour of the ground. If the boom should suddenly drop, the anti-cavitation valve will keep the rod end of the boom cylinders from cavitating. This anti-cavitation valve also protects the rod end of the cylinders when a load is lowered to the ground with the control lever in the float position. The detent assembly is attached on the end of the valve spool on the outside of the centering spring assembly. It is a typical ball and ramp type detent assembly. It consists of the carrier, a spring-loaded cam pin, 3 detent balls, a piston, guide pin, and a guide pin spring. There are 2 detent grooves in the boom sleeve and 1 groove in the bucket sleeve. When the control lever is moved to any of the positions that are detented, the balls are forced out of the carrier into the groove by the cam pin and held in place by the tension of the internal cam pin spring. Before moving from the detented float position, the cam pin pressure must be overcome by the operator. The boom raise and bucket rollback detent positions can be overridden manually, and they are also equipped with an automatic air release mechanism. When air is applied to the piston, it moves the guide pin against the tip of the cam pin. This depresses the cam pin spring, releasing the balls from the groove, and allows the centering spring to move the spool back to the neutral or hold position. This photo shows the air release mechanism attached to the bucket cylinder. As the rod extends to roll back the bucket, the bar on the mechanism also extends. At a preset position, an air valve lever, located under the protective cover, moves and sends air to the bucket detent to release the bucket spool. The position of the air valve is adjustable. A boom kickout mechanism is mounted inside the front frame at the upper end of the boom arm. As the boom is raised, the follower on the pilot air valve lever arm rides on the cam. When the boom arms reach the desired level, the cam stop positioner causes the lever arm to lift, which sends air to the boom detent release piston. The location of the stop positioner is adjustable. We'll now take a minute to review the main control valve. Stop the tape while you're answering the questions. The answer to number 1 is true. The bucket circuit is equipped with a circuit relief anti-cavitation valve on both sides of the spool. Number 2 is false. The boom raise circuit is equipped with an anti-cavitation valve only. Number 3 is also false. The circuit relief valve settings are different than the system relief setting. Number 4 is false. The circuit relief valve is open when pressure builds above the relief setting. The boom and bucket cylinders are similar in design. The only difference is the mounting and cylinder size. The major components of the bucket cylinder are shown in the photo. The one-piece piston is secured to the rod by a large self-locking nut. The piston seal, which is located in the center of the piston, consists of a Teflon seal with a rubber backing ring underneath. Wear rings are located on either side of the piston seal to protect the seal from contaminants. O-rings are positioned under the wear rings at the outer ends of the wear ring grooves. This provides a continuous positive fit at the leading edge of the wear rings. The gland assembly is held in place at the end of the cylinder tube by the 3-piece lock ring and retainer plate. One O-ring fits between the lock ring and the retainer plate. Another O-ring, with a backup ring, is fitted into a groove on the outside of the gland. Located in the internal bore of the gland assembly is a seal and a wiper. The seal prevents leakage past the rod. The wiper cleans dirt from the rod as it retracts. When diagnosing a hydraulic problem, the service person should have a thorough understanding of the hydraulic system. The service person should know what components make up the system and what the function of each component is. The first step in correcting a problem is to determine what the actual problem is. If possible, the machine should be operated by the service person to check all of the hydraulic circuits on the machine. If only one circuit is found to have a problem, then any component which affects more than one circuit is not the faulty component. The hydraulic system can be divided into 4 areas. The 4 areas are suction, system, circuit, and return. After limiting the possible faulty components to one of the 4 areas, the service person should take pressure checks and flow readings as necessary to determine which component is at fault. We'll take a look at each of these areas and the related problems. The suction area of the system is the reservoir to the hydraulic pumps. A problem in this area would be aeration cavitation, which would result in noise from the pump and erratic operation of the entire hydraulic system. The items to check would be the fluid level in the reservoir, the strainers, the suction lines to the steering switch pump, and to the loader pump. The system area is the hydraulic pumps to the control valves. The 540 has 2 pumps and 2 control valves. A problem in the system area will cause 2 or more circuits to be slow or weak due to internal leakage. The components that could be faulty in the system area are the pumps, the diverter valve, or the system relief valves. The circuit area is the control valve spool sections to the cylinders. A problem in this area would cause one circuit to be slow or weak due to internal leakage. The components to check in the circuit area are the circuit relief valves, the valve spools, the anti-cavitation valve, or the cylinders. The return area consists of all the components from the cylinders to the reservoir. A failure of one of these components will cause an engine overload or the hydraulic oil to overheat. The problem in this area is caused by a restriction of the return flow. The components in this area are the oil cooler, the orifice block, and all of the return lines. The steering system is different from the loader system as it only has one circuit. Therefore, we will divide the problems in the steering of the machine into 2 areas. First, we'll look at the possibilities of a steering problem in both directions, and then look at a steering problem in only one direction. With a problem in both directions, the possible faulty components are the pumps, the system relief valve, the directional spool, the locking spool, or the cylinders. A steering system pressure check should be one of the first checks made. A quick disconnect for checking pressure is provided on both of the steering cylinders at the rod end. To check this pressure, install a gauge with a hose long enough to allow you to stand away from the machine. Lock the frame halves together and turn the steering wheel. If you are checking the right cylinder, turn the wheel to the right. For the left cylinder, turn the wheel to the left. Check the pressure at low idle and at high idle. If the pressure is incorrect at both high and low idle, adjust the steering system relief valve. The pressure should be 2,000 psi. If the pressure is as specified at high idle and not at low, the system relief is probably okay, and the problem would be internal leakage in the cylinders or both the steering and the switch pumps. Check these components for excessive heat. If the pressure is as specified at low idle and not at high idle, the steering pump would be at fault. For safety, the steering system pressure adjustment should be made with the engine shut off. Remove the nut from the relief valve adjusting screw. Turn the adjusting screw in 1/8 of a turn to increase the pressure. Start the engine and check the pressure. Repeat this procedure until you have the correct steering pressure. If the pressure does not change, the problem may be in one of the other components mentioned. Remember that internal leakage will cause heat. Check the other components for excessive heat before replacing the system relief valve. The probable cause of a one-way steering problem is the circuit relief valve or the check in the locking spool. There is a circuit relief valve on each side of the steering valve. These valves cannot be adjusted. The front circuit relief valve is for a left turn, and the rear valve is for a right turn. The first step in troubleshooting the loader system is to take time to study what the problem is. The possible faulty components can be narrowed down just by watching how the machine functions. If the loader is slow at high engine speeds and the steering is fast, the diverter valve in the steering switch pump could be stuck in the low speed position. If it is stuck in the high RPM range, the steering would be slow at low RPM and the loader would be fast. If the loader is slow at high RPMs and the steering is slow at low RPMs, then the probable cause is the switch pump. If the steering is normal and the loader is slow at all speeds, a loader system pressure check should be made. A quick disconnect is provided on the bottom of the loader control valve to check the loader system pressure. Use a gauge with a hose long enough so you can stand away from the machine. Raise the boom to maximum height and read the pressure on the gauge first with the engine at low idle and then with the engine at high idle. If the pressure is low at both speeds, the pressure check should be made with the bucket cylinder bottomed out. If the pressure is still low, try adjusting the system relief valve. If the pressure is as specified at high idle but not at low, the relief valve is probably okay, but the loader pump is worn. Be careful when making the loader system relief valve adjustment. The relief valve is very sensitive. Therefore, turn the adjusting screw only 1/8 of a turn at a time. The main hydraulic system relief valve setting is 2,750 psi. To check the diverter valve in the steering switch pump, 2 pressure gauges must be installed. The switch pump pressure gauge should be connected to the port on top of the diverter valve as shown on the left side of this illustration. The steering pump pressure gauge should be connected at the port on the side of the diverter valve. If the machine is equipped with ground-driven steering, a line will connect this port to the steering unit. In this case, the gauge can be teed into this line as shown in the right photo. To test the diverter valve, put the bucket on demand. One way is to roll the bucket all the way back and hold the control lever in the rollback position. Increase the engine speed from low idle to high idle while watching the pressure gauges. At low idle, both gauges should read low pressure. When the diverter valve switches, the switch pump pressure gauge should increase to the loader relief setting while the steering pressure gauge remains at low pressure. The engine speed should be noted when the switch pump pressure gauge increases. If the diverter valve is switching at too low an engine speed, the set screw under the lock nut on the side of the diverter valve should be backed off a small amount. If the switch is made at too high an engine speed, the set screw should be tightened a small amount. After adjusting the set screw, remember to tighten the lock nut and recheck the diverter valve. The right photo shows the switch pump port, the steering pump port, and the lock nut which secures the set screw. The loader pump or switch pump can be the cause of a loss of power. The only way to check the pumps is to install a flow meter. The main hydraulic output for the 540 is 44 GPM at 2,500 engine RPM from the loader pump and 38 GPM from the switch pump. Remember that at 2,500 RPM, the flow would be combined loader pump and switch pump flow. So the diverter valve must be checked for proper switching before the pumps are flow rated. Let's take a look at the components that will cause a problem in the circuit area. Remember, A circuit problem affects only one circuit. The possible components are the circuit relief valves, the spools, the anti-cavitation valve, or the cylinders. A check for the proper adjustment of the valve linkage would be the place to start. A circuit which is weak or slow may have a worn spool, damaged packing in the cylinders, a faulty circuit relief valve, or a faulty anti-cavitation valve. This completes the program on the 540 hydraulic systems. Other programs are available covering this machine.